Bon, ben, bonjour. Merci à tous d'être présents à la conférence Québec-Océan d'aujourd'hui. Donc, aujourd'hui, on accueille Sam Laney, qui a eu la générosité d'accepter notre demande. So, Sam Laney is a senior scientist in the biology department at the Woods Hole Oceanographic Institution in Woods Hole, Massachusetts. He is dual trained as an oceanographer and engineer. He has spent his career working on ocean phenomena at the interface of these two disciplines. He has particular interest in Arctic ocean systems and in developing new approaches to observe poorly examined seasonal and annual phenomena in ocean biochemistry. His main focus for the last 10 years has been the coastal Alaskan Arctic, especially the annual spring freshet event. Sorry.
Right. No, that's okay.
So please join me in welcoming Sam. And today his presentation will be about observing annual, seasonal, and ephemeral processes in the coastal Alaskan Arctic.
Thank you, Caroline. Thank you. Bonjour à tous. Thank you for inviting me, and thank you for allowing me to save respect and face by delivering this in English. We could do it the other way, and it wouldn't be successful. I think what you just described is how I describe myself. So before we get into the talk, let me just give you a little background about what to expect for this seminar. And I guess the first thing to think is that I don't really think I'm a good scientist. I have kind of three different careers that I'm trying to juggle at the same time. I'm a biological oceanographer. I'm trained in that, so I'm very interested in the biology of the ocean and specifically photosynthesis. But I'm also an engineer. I have formal engineering training, and I used to be an engineer before I went back for my PhD. And I'm also an educator. So I have graduate students, but I'm also pursuing my own degree in education. And when you do this type of breadth, it's very difficult to be very good at every single one of these things. But I found that in my career, I've been able to approach interesting questions in ocean science because I'm not so specialized, but because I have this breadth. And sometimes these questions aren't only scientific. Sometimes they're innovative technologies or exploration, going to new parts of the planet and finding ways to study the ocean just to start the ball rolling for science that isn't happening yet in those regions. And so my interest in the coastal Arctic is partly driven by that. I have some interests in the biology of the Arctic Ocean and the phytoplankton and the oceanography, et cetera. But I'm also very interested in how can we observe it better, because it's not easy. And how do we bring in more people to participate in the science of the Arctic as opposed to just highly trained academic scientists? I just want to mention that I'm here with the support of Fulbright Canada. I really appreciate this program that is set up, and my hosts, Sentinel North and Institut Nordique de Québec and Takuvik. So I've been very well taken care of in my time here, and I've enjoyed meeting many of you. So let's start with the talk. Annual, seasonal, and ephemeral processes in the Alaskan Arctic, that could be anything. That's huge. So I'm only going to focus on one particular example, and then by talking through this example of an ephemeral process, you might be able to see how some of these technologies and approaches have allowed us to study seasonal and annual scale. So my primary motivation for the research I'll talk to you now about is better observing the coastal Alaskan Arctic. For us in the US, it's a very under-observed part of our coasts and our oceans. And I'm particularly interested in one specific type of event that happens in the coastal Arctic, the spring freshet. So freshet means the time of year when the snow melts off the land and funnels into the rivers and dumps into the ocean. It's short. It only takes a couple of weeks. It always happens in the spring and early summer. And in the Alaskan Arctic and in the Canadian Arctic as well, it happens at a very interesting time because even though the rivers are running, the ocean is still covered with ice, which is very different than the freshet that happens out here in the St. Lawrence, or in the rivers near where I grew up. And to drill down even further, I'm interested in how those river events, those very short but strong winter events in a very difficult time of year to sample, contribute to the biological oceanography of the coast. Those river waters are bringing a lot of dissolved organic carbon and particulate organic carbon, DOC and POC, and they set up interesting changes in the coastal waters that have not been observed. So that's the big picture of the talk. And then I will not go too deep into any specific scientific question because I know there's a very broad audience, but I'll talk first about some of the challenges, just the things you have to think about before you do this type of research. And many of you in Quebec, here at Laval, Rimouski, elsewhere, you're well familiar with these things from your field work, but I'll just explain what it's like for us on the western side of our Arctic, our shared Arctic in Alaska. I'll then talk about some advances and new approaches. And these are not fancy high technology things. I work in a space where I try to build things that are as simple as possible, which I think is very difficult engineering. It's not easy to do things simple. For example, I drive a Volkswagen Beetle at home, a 1970 Beetle. It's a putt-putt air-cooled ancient vehicle. And I love it because it's simple and it's extremely well engineered. There's a lot of thought that goes into that particular car. And I use that philosophy in my engineering research. And then at the end, for those of us who are scientists, I'll talk about some scientific findings, introductions. Okay, so let's start. I'm just going to start from a very high level about the Arctic Ocean, and then drill down to my narrow interest in Alaska. So many of you know this, but many of you don't. The Arctic is a very small ocean. It's not very big. It's not very big in terms of area. It's small in terms of area. And it also doesn't contain a lot of water. It only contains 1% of the global ocean volume. And that's partly because the ocean is small, but partly because it's shallow. If you look at maps of the bathymetry of the Arctic Ocean, you'll see that there's some deep bits in the middle, but most of it, about half, is shallow shelves. So there's not a lot of water in the Arctic Ocean. But what's interesting about the Arctic in some sense is that the Arctic receives 10% of the global freshwater input. So because it is surrounded by continents, those continents are draining freshwater, and that freshwater is coming from very far south. So Mongolia, Kazakhstan, these are nations that are in Central Asia, and their water goes into the Arctic Ocean. And so as this water is moving into the Arctic, it's bringing a lot of materials, of course, things that might be nutrients, things might be sediments, things that might be pollutants. And because the climate is changing, these patterns are changing as well. When this material shows up in the ocean, when the land is melting snow, when the rain is falling, things like that. And so a lot of Arctic oceanographers are very focused on these big six, these 6 rivers. They're called the big 6. But if you look at the Arctic itself, what's in gray is not drained by those big 6 rivers. They're drained by little local rivers. And that's definitely the case in Alaska. That's in the case of a lot of Canada and a lot of Russia. And you know, these small rivers don't get that much attention. So this has been my focus, is to look at the small rivers that other people aren't necessarily looking at and inventing new techniques to do it. This is the Alaskan Arctic coast. Demarcation Bay on the far right is the demarcation with Canada, and Barrow, Alaska on the far left. The far west is where our coastline starts heading south again. And you can see all these little rivers feeding in. I'm working in the very center of this region in an area called Stephenson Sound, which is a typical part of the Alaskan coastline. It's surrounded by some barrier islands, and it's very atypical in that that's where there's a huge oil industry, Prudhoe Bay, petrochemical facility. So we chose this area because it's convenient for studying the spring freshet. So here's just a picture on the left of what the freshet looks like from a satellite. So I've drawn in the black line of the outline of where the coast is and where Stephenson Sound is and some barrier islands that are just offshore. And I've labeled 3 rivers in blue. And you can see that the rivers are a little dark because the snow on the rivers is now wet. The rivers are starting to run, but they're still frozen over. And underneath the letters Stephenson Sound, you can see some darkness as well. That's river water flooding onto the ice, making the ice and snow wet and damp, but it's still covered. So we can observe this through satellites. We can observe the spatial changes and the temporal changes, sort of, but we really don't know that much about what's going on in the rivers themselves. And that has been part of my work, is to try to link the what's going on in the rivers with what types of phenomena we can observe from satellites, because there is no chance that we will be able to look at all the rivers in the Arctic Ocean. You know, from a remote sensing point of view, satellites are an important avenue to look at, given how broad and unsampled the Arctic is. So here's a title of a project that I started in 2016 with some colleagues, interdisciplinary colleagues, to look at the specific freshet event in the coastal Arctic. There were 3 institutions involved. There were 4 PIs, including myself, and 3 graduate students in the bottom. 2 of them are now doctors, and the guy who is kneeling defends on Tuesday, so he will better be a doctor by Wednesday, is my final student. And these are our questions. We had to scope down the science because it's so understudied. What's the first area we can start thinking about? So we said, okay, let's just choose 2 rivers that are side by side. And we chose the Kuparuk River and the Saginaw-Virtok River. They're not big rivers like the St. Lawrence. They're not even big like the Saguenay. They're smallish coastal Alaskan rivers, but they're very different because the Kuparuk drains area that is mostly tundra. And the Saginaw-Virtok goes a little bit further back and it drains tundra, but also some mountains further south in Alaska. So these 2 watersheds have very different land properties that they drained. So you might expect that they're good examples of how different rivers can be along the Arctic, the Alaskan Arctic. Plus, they're side by side, so it makes it easy for us to work on one and then the other. And so we wanted to study the spring freshet in these conditions and just to see what types of technologies are the easiest to deploy. And so we started using optical methods because in oceanography and in my field of biological oceanography and in some chemical oceanography, they have sensors now that use light to measure properties, and they are relatively inexpensive, and we wanted to see how well they worked. One of the problems with the freshet is that, especially in these very northern regions, the gauges in the rivers that measure river flow, the government sets these up in various rivers in both of our countries. Those gauges don't work when there's ice in the river. So the blue data is when the gauges are able to give us measurements of water flow. So on the top is the Kuparuk River for 3 years. In the bottom is the Saginaw-Virtok for 3 years. And you notice that the data become good only in early June. And this is when the freshet is happening. So we are already at a disadvantage because we don't know how much water is coming out of the river. We don't even know the timing of when it will come. We expect it to be early, and the government will give you a guess, but they don't know. It's just some extrapolation. It's just some guess. There will be a red line there that says, oh, this is what we think it is, but it's not real data. So this is already a disadvantage. To give you, and so here on the bottom left, you can see one of the examples of those guesses, like, oh yeah, there's a big freshet in the blue, but it's not real data. What it will look like too is also very, if you start seeing pictures of the freshet, you'll understand why this is. So this is the Kuparuk River is, if you see on the left, there's a road and there's a stop sign. That's where there's a bridge, and the river is going under the bridge from the left and it's flowing out to the right past that little point. We were up there, fortunately, one day before the freshet showed up, which is great for us because we could measure it. Oh, we were very excited. We know it's going to happen. But when we showed up the next day, the freshet had completely destroyed the road. The ice had washed out anywhere we could sample. It was extremely dangerous, even for us on foot. So this is why once we started seeing this, we were more charitable to our colleagues in the Geological Survey who work with the stream gauges. It's not an easy problem, and it's not one that we tried to solve. So yeah, this is what happens when, all right, we're back. Yeah, the freshet apparently even affects the projector. But yeah, this is the type of magnitude of what it can happen and how quickly it happens. So a satellite might miss these events if it's only measuring once a day. Like, these are very short and very important. Half of the fresh water that goes into the coastal ocean each year comes during this 1 or 2 week period while the ice is there. So we first started out looking at what we could see from satellites. And so this is just a few days, maybe every other day in May 2019, of what these freshets look like when the water spills out into the ocean. We saw the Saginaw-Virtok earlier, but the Kuparuk has not yet started. And for those of you who have done satellite work in the Arctic, you know that the Arctic is very cloudy. And that affects these types of measurements. It's you know, we one of our challenges is trying to figure out what type of data are even collected in this picture for us to understand the freshet. And one important problem is that what we see on top of the ice might not represent what's underneath the ice. So the water is fresh coming from a river. It'll ride out on top of the ice, but it also squirts underneath the ice in a freshwater layer that sits on top of the ocean, but underneath the ice. And we have no idea where that is from a satellite. It's a hidden problem, which again is a good reason to do research on the ground or on the ice. So this is research on the ice. We first developed a research program, and it will happen in sort of 3 different steps each year. But one of these important steps is being able to measure that fresh water from the rivers underneath the ice. So we here are in a room with a white ceiling. I often use this as an example of what it's like under the ice. If you can imagine that you're in the ocean and the ice is above you and we're looking at the bottom of the ice, that up there is where the freshet is going to be. It's not necessarily going to be down deep because it's going to be riding on top of the denser seawater. So you need to put instruments up there. So we developed a buoy system that we could take out to the coastal sea ice by snowmobile, drill a hole, stick it in through the ice so it just sticks down into the ocean below, and then that will freeze in. And if we do that before the freshet, then we have something in the ocean ready to do some measurements when that freshet water squirts underneath our various stations. I'll just talk a teeny tiny bit about the instruments that we use, these optical instruments. Optical instruments, I guess they're great. I've worked with them for 30 years, but they don't give you often direct measurements of things that you care about. So I chose to study the particulate organic carbon and the dissolved organic carbon in water, but there's no dissolved organic carbon optical meter and there's no particulate organic carbon optical meter. We have to use proxies instead. So for particulate matter, we use optical backscattering. So particles in the ocean reflect light when you shine it, and the more particles, the more light you get reflected back. So that was our first proxy. And then dissolved organic carbon is often thought of or measured as something like called colored dissolved organic material. If you can think of like lakes in the summer, they look kind of brownish like tea. That's CDOM. That's dissolved organic carbon. And it has an interesting property where it will glow blue if you shine ultraviolet light on it. It fluoresces. And you can have instruments that measure that as well. And these instruments are not, I mean, I don't have anything in my hands, but they're smaller than 2 C-cell batteries end to end. Like they're not big. They're maybe, this long and this big around, and they don't take a lot of power. And that makes them good for putting in the little sensor clusters that you see in yellow on the end of that stick, which will stick right below the ocean ice interface. So we don't want to use low-cost sensors. I mean, we're not being cheap, but the more low-cost sensors you use, the more you can buy. So it's one of our philosophies of measuring broadly across the Arctic is don't use the expensive stuff, because for every one expensive thing, you can buy 10 cheap things and measure 10 sites instead of 1 site. And then, of course, the other thing is you'll probably never see these again. So you're just throwing stuff into the ocean, and you should be respectful for that. Just a little point about the picture on the bottom. Most of us who work in ocean science in temperate waters, warmer waters, we worry about biofouling, stuff that grows on your sensor and makes your sensor give you bad data. And in the Arctic, it's less of a problem because it's colder, and so organisms don't grow so quickly or foul your instruments. And then this is actually one that we recovered off the beach about 5 months later, showing you that the faces are nice and clean, and we can trust our data. And of course, when we are putting these in the water, we're also doing lab work on our ship to calibrate them against more sophisticated analytical chemistry methods of measuring POC and DOC so that we know what the real data are. It's good to ask the question before you do any research, what do people know about it before? And I say that it's not very well studied, but we can actually show that. People have looked at the temperature and salinity extents of the spring freshet when there's still a lot of ice. So in the left-hand picture, you see a line that's going sort of, I don't know, up till 1 o'clock past station Dinkum towards Station Cross, which is near Cross Island. That line is a transect that's shown in the right-hand panels going from inshore to offshore. And you can see the ice at the top is a meter or a meter and a half thick. That's safe to work on. You can make these measurements. But when the freshet shows up, the ice is no longer a meter thick. So we don't know what happens later in the season. We know what happens early. Previous people have looked at it. We also know that people have looked at these two different rivers for their chemical signatures, but again, very early in the year. So we do know that they're different so that when we cite our stations that they're in front of the correct rivers. But it's complicated for those of you who've worked on rivers before. How river flow goes under the ice, nobody knows. So we had to be careful to put those sites in proper locations. And then in terms of the optics, like, are these instruments going to give us useful data? Really, there is nothing known. I'd say this research was one of the first to look at it in this part of the Arctic. That was part of the reason we got funded, actually, is because the agency that was funding us, NASA, before it invested in giving lots of other people money to buy lots of other sensors, it makes sense to know if they work in the first place. So my project did some service to the community by taking many different types of sensors out there and seeing which ones work and which ones don't. Some of you might also know that there's a big program in the United States studying 3 lagoon systems across the entire Alaskan coast. They're long-term observing systems. And my work happened before these were set up, even though people in those projects were working there earlier. But again, it's a very comprehensive scientific study that they're doing, but it's not really focused on observational approaches or the freshet time of year. So this is just some background about the level of sophistication of this type of science in the United States today. And also, just to drive the point home, what we know is just this little tiny box that we're studying, what I just described as only a little bit of the Alaskan coastline. There's no reason that this type of behavior or phenomena should be the same around the planet in all these other gray areas. Okay, so let's talk a little bit about the strategy for observing the spring freshet. I said that I had some, I did things in different stages to try to get the freshet in spring, but in order to do that, I had to put sensors out at other times of the year. So I was actually measuring a lot of different times of the year just so that I can get the measurements of the spring freshet. But primarily, we did 2 main types of things. On the left, you can see us deploying a bottom mooring. So that green frame contains sensors, and we throw it over the side of the boat. It sinks to the bottom. Those sensors, some of them measure the water immediately. Some of those sensors, there's acoustic sensors that look up and help us understand the water column above. We put those in August when there's no ice. So we can actually go out there with a boat. And then we come back the next August and we fix them or take them home. But obviously August isn't the freshet, and we wanted the information right below the sea ice. So we go out on snow machines in late April or early May before the freshet, put some of these ice buoys directly over the moorings that we had planted the year before, so that we have something on the bottom and something underneath the ice at the same place at the same time before the freshet shows up. And both of these, the ice buoys and the moorings, as much as possible, we tried to have similar instruments on them. So in order to catch these 2 rivers, we needed an array of locations across the front of them. So from the furthest west, there's something called K1. It was one of our stations. The furthest east was a station N1. And then we had 3 stations in between, in front of the rivers. And then we had 1 station outside the barrier islands, station S2, to give us the ocean characteristics as end members. We have freshwater coming in from the land, and we wanted to know what the ocean looked like so that everything in between, we understood what the boundaries are. And this is, this what you're looking at inside the barrier islands, I don't know, maybe 800 square kilometers. So this was a lot of surveying the ocean coastally, just to bracket these rivers along the coastal margin. This is what it looks like in time. So we know that in 2017, when we started, the freshet had showed up in May and June, and it will show up in May and June next year. So in August and September, we put our moorings in. The next April 2018, we went out on snow machines and installed ice buoys. Then the freshet arrived a few weeks later. Then in August, September of 2018, we went out and recycled our buoys, our moorings, and we also picked up any of the ice buoys that had drifted and found their way to beaches. And that set us up for 2019 when we were able to go out and put our systems in again. But in 2019, we were very lucky or very unlucky. I'm going to say lucky, but I'll show you why in a second it's unlucky. We're very lucky in that we were just a few days in front of the freshet. So while we were there, we could actually drive along the rivers and take our ice buoys and just throw the sensors in the rivers and say, if the ice buoy were in the river, or if the ice buoy was sampling 100% pure river water, what would that signal be? And then in 2019, we pulled it out. So let me just talk more about the challenges. I said a second ago that maybe it was an advantage or a disadvantage to be there right before the freshet arrived. The picture on the top left shows kind of the disadvantage part. So that's us trying to put a buoy through the ice, and we are standing in about this much water, which means the rivers were already running and things are getting dangerous. So the day after would have been stupid to go out. So it's, as some of you know, it's expensive and difficult to stage oceanographic field work, even if you're using autonomous systems like these buoys. Now, I'm not going to go too much into the technical challenges. I assume you already have some internal feelings, some gut feeling about why technology that works great in other parts of the planet won't work great in the Arctic. And part of it, of course, is it's cold, right? Instrument manufacturers, they don't sell that many instruments to people who use them in the very cold. Well, why would they bother? So we have to pick and choose as scientists which ones actually will work. And I never took that for granted. In fact, I thought it was probably safer to think that they won't work. So, being able to test them at home in cold chambers gives you some idea of when they will stop working. But the cold is only part of the problem. In the lower right, you see some optical measurements using an instrument called it's called a triplet because it has 3 different types of optical sensors on it. But this is an instrument that sat on our bottom mooring, and the 2 bottom panels show an entire year of time. And in the top panel, very early on in the year, and later at the other end, when we pulled it out, you can see the numbers are high and almost off the screen. That's because these instruments weren't really developed for the type of dirty, murky, ugly water that's coming out of these rivers. They're designed for clean ocean water, relatively clean ocean water. And so for those of us who are interested in these properties, this is an actual photograph that the NASA Arctic Colors program does when they try to describe the optical complexity of these rivers in the Arctic. I think this is around the Yukon, so further south around Alaska. But this isn't necessarily ocean biology. There's land dirt in there and other things being carried. And this is a big technical challenge for us. It's not a type of water that instruments are designed to measure. Another thing that some of you may appreciate is that the coastline where we have in Alaska, it's shallow, it's narrow, only a few tens of kilometers before you get to deep water, but it's still too shallow for our research icebreakers to go. Partly it's because it's actually too shallow for them to go, and partly it's because our icebreakers like yours are run by the Coast Guard. And if you're the Coast Guard and you're in charge of ocean safety, you do not want to be in the newspapers for getting your ship stuck. So this is very sensible. I get it. And very expensive if you make a mistake. People's careers will be, senators here, there's presidents here. So this whole area, I've put in the little skull and crossbones just to say ships don't go there. So we have this basic challenge of anything we want to do, we can't have a ship. So it's a very different way of thinking. And even when we do have a little boat, so there's actually now up there's 2 boats the size of what you see in the picture on the left. It draws a little less than a meter of water, so it can go anywhere deeper than a meter. Even if you have a boat like that, what the picture on the right shows that you can't quite see is a purple track that seems to go across a piece of land. So that just shows that the charts are wrong. So this is yet another complicating problem, is we really don't have a good idea of what the ocean and the islands look like, because it's wrong because there used to be an island there. It's just shifted because it's a sandy barrier island. Over 20 or 30 years, it's moved a little bit, and the bottom scours as well. So when we're trying to design moorings to sit on the bottom of the ocean, we're looking for these little pockets that are maybe a meter or so deep that we can hide our mooring in, so that when the ice comes along, the mooring is protected. Because these waters are not that deep. They might be at most 8 meters. And you can imagine a keel of ice scraping along the bottom, destroying your mooring. So just finding a hole to leave your sensors is challenging. It's a challenging logistical question. One of the things that we do have an advantage in this area comes from the fact that there is this huge, immense national scale oil drilling complex up there. It's a town of nobody but oil drilling people. And that means there's jet service there. There's an airport and 737s fly in. And there's also a road with, big trucks. So you can actually get equipment to this area easily. But we were very cautious to not rely on that in our long-term vision. That was great for doing our experiment and making it convenient. But we knew that the other villages nearby where we might want to go certainly didn't have this type of capabilities. So we made sure that when we were inventing technology, we addressed questions like, how easy is it to put batteries in this? Because some batteries can't go on small planes. Like when you buy from Amazon and you buy something with lithium batteries, there's a little stamp in the front that means it didn't go on commercial aircraft. It has to go through different shipping routes. And in North Alaska, the pilots get to say whether they want the stuff on their plane or not. So we had to re-engineer our thinking to not use the best stuff, the technically best stuff, but the stuff that could actually be delivered to the field, which makes our technologies a little more applicable. And so we're very mindful of those privileges. We made sure not to take advantage of them too much. These privileges were very helpful, though. We were able to use the entire road network within the British Petroleum lease area. That allowed us to get in a pickup truck and drive to a river and sample it. No helicopters, no walking through the woods with bears. There was also, you can see in the upper right, there's this plant out on a spit. Along that strip of land heading backwards, heading south, there's a boat dock. So we can actually drive right to the ocean, right to the Arctic Ocean. And when we're cold, like when that's covered with snow in the winter, we can drive the snowmobiles into the building and warm our hands. Like this is really nice, but it requires working with an oil company. And it's not like scientists are bringing them a lot of money for profit. We don't have the type of money to pay the oil companies to do helping us. It just doesn't make any sense for them. We have to work with them in a different type of relationship. And, there are drawbacks, as I'm sure you've experienced in maybe some of your research. A big company like British Petroleum has very complicated safety training. We spent a day in Anchorage, Alaska, getting trained for oil field safety. There's a lot of paperwork, environmental impact statements, because this is an oil industry. They do not want to make mistakes. But the advantages are we have really nice access to some of these field sites. You can see in the center at the bottom, a water treatment plant that sticks out in the river. You could put instruments on this thing. It has internet, things that the governments don't invest in, private companies do, or laboratories where you can do real chemistry. Oil industry has that. So that was a benefit to us. And of course, this is British Petroleum. So when we would have to go and talk to their bigwigs, we would go to this nice building in Anchorage, and they would have Wine Spectator magazines. It was just ridiculous. Just the level of wealth in their waiting room. This is my colleague, Steve. We don't read Wine Spectator at home, but we always look forward to the trip to BP because we could read while we're in the conference room. So let me just talk about some of the political challenges, and I say mammal challenges too. In the area that we were working is one town, effectively one municipality called the Alaskan North Slope, the North Slope Borough. So all of our permits to do research had to be passed through the North Slope, and people on the North Slope, various communities still do this. So they do subsistence whaling, and this whaling happens in the area in Stephenson Sound where we were working, just at a different time of year, a little later in the season, passed into September. So we worked very closely to make sure that, first of all, we weren't there in the way. And we also made sure that all of our equipment was gone. So the beach on the right is not too far away from the beach on the left. So in August, I was on the beach with my colleagues, finding out where the GPS told our sensors were, collecting those instruments off the beach and putting them back on the boat to take them home and disassemble them, because I look at those things and I say scientific equipment, but people from the village of Nuiqsut nearby look at those things and they say garbage, because at that point it's just broken stuff on a beach. So we wanted to be very thoughtful with our instrumentation. And so when we built things like the buoys, we actually developed them so that they could be disassembled and recycled in a sense. So the big white thing that I'm dragging, the white part, is actually a float that you put in the harbor with a weight to moor your little boat. So once we ship those up and we're done with them, they're useful to other people who have boats in local harbors. Or other pieces like the strut is actually commercial grade strut channel. You know, we have it in this building. People can use that. So when we're done, we have something to give back. We're not just making garbage. And of course, there are other mammals that we care about. This was right behind where our boat dock was. It's the very north end of the Alaskan pipeline. So this goes, like, oil is coming out of the ground just off to the left, and it ends up in Valdez, Alaska, several hundred miles to the south. And, you know, we have to be, of course, concerned about how animals, other types of animals than whales, interfere with our research. So that, you know, that I hope gives you a taste of the sort of the scope of the problem or the environment in our side of the Arctic when we're trying to do research at this unusual time of the year. And I'm just going to quickly sort of hit on a couple of the technological advances out of all this work. What do I think is the most valuable, or what has the most use in future projects? And so, you know, we, like I said, did a lot of things: 3 mooring cruises, 2 ice buoy deployments, and land-based sampling. A lot of this is being turned into scientific publications. But things like this ice buoy, I've had a lot of interest in other people who want to use it. The fact that it is easy to deploy, you don't need a specialist. I mean, you need somebody who can make the holes, somebody who's stronger than I am. And it's designed so they can use various different types of sensors, not just the ones I used, but it's very general. We've had people interested in this. The idea that these sensors work, people are now thinking about using some of them in other applications in the Arctic. And so I actually gave them grades, like the Turner instruments were, you know, A minus. The CTD got a C+. It was not all that great. Some of the other sensors that we thought would be good, you know, we now know a lot more about their performance. These buoys that we develop, these very low buoys that sit in the little pockets on the bottom of the ocean, they've been very nice, and other people are interested in those. You don't need a big boat to deploy them. But even if you don't have a big boat, I mean, I consider that large. I know it's not a ship, but it's large. It has a frame on the back. Even if you don't have that, we experimented with a bunch of very simple things that you could effectively deploy from a kayak. So just a little piece of weight and a stick with a float on it that you could strap an instrument and just throw it over the side of a small boat and then retrieve it with a rope and a grapple next year. We did some experimentation with even simpler stuff that we're very pleased with how it came out. The fact that these sensors behaved so well in terms of not getting fouled in terms of their faces was very successful to us, and helped convince other people that the data that you can measure in this environment will be good, even though things are left out for a year. I'm a very critical person when it comes to instruments. I would have the same concern about somebody else's project. And if they showed me clean faces after a year of deployment, I would feel comfortable that the data are probably good. And so I realized that the audience is very broad, and I didn't want to drill down into any specific of the research findings, but I wanted to touch on a few just to give you a flavor of the science results that have come out of this. And the first thing is to just, you know, sort of maybe remind you that this is 4 years of research with many groups. So there's a lot of papers and stuff that have come out of this, and I'm not going to try to cover all of it today, but just a few things of these various activities that we were doing over different times of the year in these ephemeral, seasonal, and annual scales. So the first thing is just sort of looking at how the physics of the region behaves when buoys, when the ice leaves. So the freshet is showing up, it's bringing nutrients and fresh water, but it's also disrupting the ice. And our buoys don't just measure the ocean, but they have GPSs on them. So they're moving around and we can track where they go. So the top is a timeline, and red is when we don't have any measurements of freshet. And in the bottom panel, you can see where the buoys are located. And this is when we know the ice breaks out. You know, we're able to see where the different buoys are moving in this region. We can actually see them when people collect them and bring them back onto land. And we can then call people and say, will you please pick up our buoy? Or it's behind your trailer. I can see it on Google Earth. But that gives you an idea of the timing and the distances that these parcels of water are moving in the spring. And we had one that didn't work, but we covered 3 more. And then one we lost, it was heading to Russia. We were able to track it for several months, and it must have run out of batteries. By now, it might have come all the way around. It might be in northern Quebec, for all I know. If you see something that looks like a buoy in your research, please let me know. But we could, this type of information, these maps are valuable to people. Not to me personally. I'm not interested in this, but I'm always as one of the first people in this area thinking about what the data we collect can be useful to other people. That's part of the pleasure of having an interdisciplinary team. Things that I'm particularly interested in were the fluorescence measurement that I think has something to do with dissolved organic carbon, and the optical measurement of backscatter and how those look underneath the ice when the freshet arrives. So I spend a lot of time looking at, or have spent a lot of time looking at these types of plots that show temperature on the top when it's around -2, that's salty, near frozen ocean water. And then you see a sudden change within a day to near zero water, which is the fresh water showing. So I know when my freshet shows up. And then I can look at these optical properties after that freshet shows up and look at these relationships between these 2 parameters and understand when they're moving in concert or moving in different ways. So understanding that there might be many phases to the freshet. It's not just one type of pulse, but it might be an early runoff followed by some other type of material, followed by some other type of material. And there's reasons for that I can talk about later if people are interested. My colleague Steve, who unfortunately has passed away, but he was a great colleague to work with on this. Part of what he was doing is using these physical acoustic sensors to help us understand what was going on at the ice-ocean interface by using sound from these instruments placed on the bottom of the ocean. So he was developing technologies that could look at how the ice thickness changes over time. So in the bottom picture, the ice bottom is the area of very strong acoustic reflectance. And you can see that it shallows towards spring because that's the ice thinning. But he was also able to see this new feature of some interesting strong acoustic reflection deeper in the water column that it looked like it increased over time. It got deeper and deeper. And we were able to determine that is the interface between the ice water, the cold fresh water, and the ocean water, because when the fresh water shows up, it's 0 degrees. It touches this -2 degree water of the ocean and forms little ice crystals. So just by using acoustics, we can see where that boundary is between the river water and the ocean water. And that's actually, I would say, maybe one of the more interesting results from this entire line of research is when this is happening, you do not want to be on the ice trying to measure the depth of the freshet. So no one knows how deep it is. The only measurements we had were from earlier when the ice was safe to stand on, and people thought the freshet was not that deep, maybe 2 meters. We found that it was at least twice as deep, and we wouldn't have been able to even study this if we hadn't done some autonomous measurements like this. There's no way a human could do this. These autonomous observing methods are the way to go to study this particular phenomenon. I'm spending time looking at how these optical signatures look in front of different rivers at these different sites. They're not all the same, but I could say that what happens at K1 looks sort of like what happens at SN1, but in front of the 2 rivers themselves, the patterns are different. So the patterns sort of look like this. These types of interesting things that might be happening due to the Stamuki zone that is lying offshore where the ocean ice is crumbling up against the landfast coastal ice. With my student Luca, we've spent a lot of time looking at a PCO2 sensor, so the dissolved partial pressure of carbon dioxide over the entire year, and trying to learn how that relates to different physical phenomena that happen in the ocean, in the coastal ocean during those periods. We were able to use these year-long measurements from the buoy to look at the ocean and kind of convince ourselves that there are 6 different phases that happen over the year. You can consider that there are 6 but 6 different types of ocean environments that Stephenson Sound experiences between. It's not just ice covered and ice free, and it's not just ice covered, ice free, and the freshet. There's more going on, and you can see that once you have these instruments in the ocean measuring continuously over the year. We were able to use some of these data with models to try to understand why, for example, the partial pressure of carbon dioxide changes the way it does over the year. Which of this is physics? Which of this is biology? Which of this shows maybe some other phenomena that are happening underneath the ice that we weren't aware of? And then we were able to learn a lot about what happens in the rivers that are sending water into the ocean. So when I had my student Luca go up and actually take our instruments and put them in the water, I gave him a truck, and he was able to drive a couple 100 kilometers up one of these rivers along the road and sample and bring us back information that helps us validate our instrument. So, a very simple thing would be, okay, Luca, stick the instrument in the water, take a physical measurement, go back to the lab, measure the DOC physically on an analytical device, and then compare it. So we were able to make calibration curves, which is what you see on the left, which is great. But we were also able to take some of those samples back and run them through more advanced analytical optical instruments like a spectrophotometer. So I have a spectrophotometer. We were able to put the water in and look at the different types of chemical constituents in the river waters and start teasing apart how those affect the optical measurements we make and what they might tell you about the ocean chemistry of this material that's going into the ocean. So Luca has spent a lot of his dissertation doing analyses of these types of pictures and sort of teasing them apart into their base components, and then making comparisons, like you see on the right, of how do the different components of this optical material, what's their relative contribution to the entire dissolved carbon pool. So interesting chemistry. And then linking these to how do these signatures look when they get into the ocean? So not just the river water, but there's different material in the ocean, different types of organic material. And since we're interested in this boundary layer, this boundary region, we have to look at both sides. The last sort of scientific area that we were working on was the bioavailability of this dissolved organic carbon. So some organic carbon can't be used by microbes in the ocean. It's just chemically resistant to being used for biogeochemistry. Other materials are. So we wanted to know in the river, what is the relationship between this material? Because if it's mostly unavailable when it gets to the ocean, it doesn't matter. It's just stuff in the ocean. If it's available when it gets to the ocean biology can use it. So my colleague, Krista Longnecker, who's in our chemistry department, was looking at these relationships. And in the top left panel, you can see that for the Kuparuk River over May, the black line shows when we know the freshet showed up. And you can see that there's a difference before and after in the relative contribution of the bioavailable material. Before, it's all ocean, not a lot of biological material. After the freshet, like half and half. So this is really valuable to us to be able to get these types of chemistry measurements and to go along to help us understand the ecological impact of these events. Krista's also done some very interesting work that I hope she'll be publishing soon. I know she's working on it, but looking at where this useful organic material is. Is it dissolved in the water, or is it associated with some of the particles that we've just been assuming are dirt? Maybe those particles have a lot of organic material on them that's useful. So let me wrap up. I'm happy to talk about any of those data later if somebody wants to, or email me if you'd like. I can certainly, if I don't know it, connect you up to the people who are specializing in this. But let me just summarize some of the science. We used autonomous approaches. We wanted to have things making measurements while we were at home. And we believe that these simple but elegant, I say elegant, simple but elegant approaches are providing really valuable insight into a part of the coastal Arctic during a time of the year that we really didn't know that much about. The sensors and stuff, they work, they stay clean. The proxies that we measure seem valid. When we put them on calibration curves, we get lines that we can understand. We can see temporal changes that we know relate to when the freshet is there and not, and those make sense to us. And then we also see differences between the two rivers that make sense to us. So these are all very good, rewarding, positive outputs of this type of research. But I just, before we close, wanted to make sure that I underscored that there's more going on than the science. You know, there are these new strategies for studying the spring freshet, but there's more going on than the spring freshet. And, you know, we're always looking to work with people who can see some overlap with what we're doing and working together to study other problems. We are very interested in moving forward with this idea of whatever tools that we use, that they're harmonious with local stakeholders. It could be local communities. It could be, in our case, the oil industry, but we're looking for that type of harmony with people who are really valuable to our success in science. You know, what we've developed can be scaled out. Maybe when I started in this field 10 years ago, I had visions of, you know, pan-Arctic. And I think at least for Americans, working with people in Russia right now is very difficult. But working with people in Canada is not. And that's one of the reasons why I've come to Laval and visited everybody here and are speaking out to other people in Quebec to see where these ideas might resonate in Canada, given what we've been practicing or trying in Alaska. And you know, this breadth of seasonal measurement, I think, is good. It helps people understand that there's more going on in the oceans than when you are able to go there. We have these mindsets that are shaped by what we're able to do. And it's just unfortunate. I think sometimes it narrows our understanding of what's actually going on in the Arctic Ocean. And you know, these cross-sector linkages to the oil industry and to local communities and to other universities have been very valuable, not just for me and my group, but for Arctic science in general. I'm not going to go through this entire list. I have so many people who I could thank about this. I just have a slide that could take 15 minutes to read if I really wanted to get into it. But this is not just me and my collaborators. There's many other people from many other walks of life who've helped make this successful. And that's one of the reasons why I like doing this type of work, is intersecting with people outside of my field or outside of my profession, and seeing how those types of expertise link to improve what we know as scientists about the Arctic. So thank you for your attention. I'm happy to field some questions. I'm also, like I said, happy to answer anything over email later or dropping by for those of you here at Laval in my office upstairs on the 4th floor. So thank you for your attention, and for you folks on the internet, I appreciate your attendance. Thank you very much. Yeah.
So thank you very much, Sam, for the presentation. It was really interesting. So we can take a couple of questions. Are there anyone in the room that has questions?
Thank you, Sam.
Yes.
What happens now with that data? Do you plan to expand it to some other areas?
Yeah.
I would see a place like Iqaluit benefiting from
Exactly.
that kind of data.
Yeah. So there have been two forks in moving ahead. One is definitely talking with people in other nations who are building coastal observing sites. So, you know, there's a cable observatory here in Canada in Cambridge Bay. That's one site, but it's a very different type of ocean there. There's systems being implemented, infrastructure being implemented here in Quebec, and it's a very different type of ocean. So I'm very interested in seeing how what we've learned can be modified, changed, simply used, and collaborating with other people moving forward. So there's definitely different types of the Arctic to study, and I'm very interested in those types of conversations. But the second fork is that because we were so successful with this project through NASA, this was funded through NASA's carbon cycle program. It's all about carbon cycles on land and in the ocean. And so we studied carbon and a bunch of other things that we just sort of told them we were going to do. But yeah, we're primarily looking at carbon. By the time we were in our second year, the program managers at NASA had said, you have a very successful interdisciplinary group. Please create a project that we can fund to do interdisciplinary science for our interdisciplinary science program. Yes, sure, we can do that. So we had a follow-on project to this that is still ongoing with a slightly different team, building on what we had established in terms of our capabilities to study, in this case, just the sea ice. So there was a growth also. So what I'm trying to say is there's definitely growth in looking for new collaborators in space, but there's also growth in terms of how our group learned to work. And I have to say that's been one of the really nice surprises about my past few months here in Quebec is that for some reason, and I think a lot about this, for some reason, this ocean community in Quebec is tightly connected in an interdisciplinary way that I don't know I've ever seen anywhere else, anywhere that I've worked in the past 30 years. I'm really excited about that. And so I don't know how to describe how you can go forward with that type of thing. For those of you who are interested, there is a seminar this afternoon in this room that I'm giving on interdisciplinary science for Sentinel North. Please come if you want to hear more about how those types of things can be built into careers. But I think it's an interesting avenue that we shouldn't miss, that this is still very interdisciplinary science. You can move it to somewhere else in location, but you can also move it to something else in the type of research that you're bringing together. I'm happy to work with anybody. I mean, physical oceanographers and geochemists are great, but there are 100 other different disciplines out there that could be doing some fun stuff with us. So that was a long answer to a short question, but a great question. Thank you.
You had access to the old companies place. Was it difficult to get the old companies to collaborate with you? Did you have to convince them?
Yeah. So that's a great question. There was a lot of, I don't know how do I say this. I was put in a very interesting position. So in order to purchase people to come and help us with field logistics, we would have to pay the contract at the same price that those people would charge the oil industry. If the people, these logistics support people, were bringing out scientists, it costs as much as if they were bringing out oil company people. So the cost of our logistics was really high. And so when I talked to my program managers at NASA, they were shocked. Wow, this is too expensive. So it wasn't just the oil companies I had to communicate with difficulties. It was communicating to some of the scientific program managers in the US about the reality of doing work in these areas. They know how to work in Antarctica because it's all our science agencies. They don't know how to work with the oil companies because oil companies oil companies make money, like tons of money, but they make a lot of money. That's their world. So before I talk about the difficulties with the oil company, I just want to say there were difficulties talking with the program managers too, who were very scared to pay this amount of money. Why does it cost this much? Well, because that's what the oil companies pay these people to work. When I worked with the oil companies, it was actually quite easy, and it was a benefit to work with them, and for two reasons. One is the people who are on the ground in the field really like working with scientists. It was a real pleasure. Once you got there, once you showed up, we're different. We're new. Sometimes the scientists bring up dogs to do seals, hunting for seals, to sample for seals. Like the people in the field really love that. So on the day-to-day area, like once they get the approval from above, piece of cake, they're happy to help. It's that approval at above that's a little awkward. When we were working first with British Petroleum, it was easier because British Petroleum is a big company with a lot of money to spend on environmental safety and public relationships. And so they already had a system built in. Since we were working up there, British Petroleum has sold their entire investment on the North Slope to, let's just call them tier 2 company, like a company that it's no longer so profitable. So British Petroleum is gone. The new company comes in. They maybe don't pay so much attention to some of these things, and it's a plus and a minus. It's a plus in that there's less paperwork because they don't care. So the paperwork is easier because you don't have to fill out the environmental reports. But it's more difficult because you don't have those really professional full-time people there to help you. So it's difficult in a couple of different ways. Companies have different cultures, just like institutions, academic institutions have different cultures. So learning how the company's culture is an important part of creating these strong relationships. It stands to reason. I'm sure, like, once I describe it like this, it makes sense. It's obvious, but it wasn't really that obvious to me when I started working with BP, how different the different companies were. But the very, very short answer, it was an absolute plus, an absolute benefit working with the oil companies. That's a great question. You know, when you're starting out projects like this, it's a big source of risk. If British Petroleum woke up one day and said, you know, we're through with NASA, they could do that. So there's a lot of politics involved in being a good partner.
Thank you again,
All right.
Sam Laney.
Thank you for coming. We appreciate it.